Alright, silly people, here's the situation. We have a potential, um, which is now just the same potential that we worked through in the last problem, just reflected over the x-axis. So now instead of it jumping up to a potential v naught, it's jumping down to a potential v naught. And we need to calculate a couple of reflection and transmission coefficients for a couple different cases. Um, for both of the cases that we're going to talk about, we're going to have E greater than V naught. And since we ended up with, or I guess I should say, E is greater than 0, and then by, uh, you know, the fact that the potential is negative, E is always going to be greater than the potential. Um, so if you look back at the last video, at some point we calculated the reflection coefficient for a similar case, which was this root E minus root E, and it was minus V naught in there because we had a positive step potential. But because now we have a negative step potential, we now have a plus right there because we're just going to flip the sign like we did in the problem setup. So we have that reflection coefficient. And also, Griffiths gives us a number for the energy, that being that it's V naught over 3. So we can just quickly calculate what the reflection coefficient is. So that's going to be square root V naught over 3 minus square root V naught over 3 plus V naught, right? And then all over V naught squared. And this is to the fourth. So what we're going to do is we're going to, first of all, simplify the stuff in the parentheses by adding up the stuff in the second radical. So it's 1/3 plus 1, so it's 4 V naught over 3. We can factor out a square root of 1/3 from the parentheses, which means we'll have a just root V naught minus 2 root V naught, because the square root of 4 is 2 to the fourth, and then on the bottom we'll have root 3 to the fourth V naught squared, right? And so obviously 1 minus 2 is 1, or minus 1, so that's what we're left with on the top side. And then this, if you square root 3, you get 3. If you square it again, you get 9 V naught squared. And so we have V naught squared over 9 V naught squared, so 1/9. So the probability that if a particle is coming from the left in this potential, that it gets bounced back is exactly 1/9 in quantum mechanics. Griffiths draws a little cartoon of a car on this graph to demonstrate, like, the idea that that this isn't a classical problem. I wish that my tablet would work. There we go. Little cylinder there. Whee! I'm the Bob Ross of physics. Perfect. Little door there. So there's your car. Is this the exact same as a car falling off of a cliff? The answer is no. It's kind of a silly cartoon, really, because remember in classical mechanics, or even you probably learned this in physics 1, that the potential for a object falling through the air is going to be minus mg times whatever height it is. So let's say x for now, but that's a linear equation. It's not going to be an exact drop off. Rather, it's going to be sort of a line with a slope mg until it reaches v naught. And then, assuming you've hit the bottom of the hill, you're stuck there. All of that to say, if you try and drive off a cliff, you probably don't have a ninth chance to bounce back from the edge of the cliff. That's just not going to happen. So treating a quantum mechanics problem like a classical allegory isn't always a super viable thing to do or worth doing. So the next part of the problem asks, what if you're in a fission reactor? Hello. And fission occurs, you got a free neutron flying out of one of the nuclei that gets fissioned, breaks apart, and then it happens to get right in the path of a nucleus that is full of protons and neutrons. And it's asking us, what if we wanted to calculate that the neutron tunnels into the nucleus and ends up having more fission, like a chain reaction? Well, again, we sort of did this problem already because it's the same sort of plot, right? The neutron is experiencing what is essentially zero potential outside of the nucleus, but inside the nucleus, it is experiencing a potential of minus 12 mega electron volts. So this is 0 here. And so again, the reflection coefficient is going to be R equals root E minus root E plus V naught, both under radicals to the 1/4 over V naught squared. And then the problem statement gives you a kinetic energy that the neutron has, and because it's experiencing zero potential outside of the nucleus, it will have a total energy equal to its kinetic energy, which in the problem statement was 4 mega electron volts. So we have R equals root 4 here minus root 4 plus 12, all in units of mega electron volts. And so we get a unitless answer. This is 4, no, it's 12 squared. So that's going to be your reflection coefficient. The problem asks for a transmission coefficient, though, so if you need that, all you need is the fact that t plus r equals 1. You can solve that for t, be like it's 1 minus r. So you'll find that the transmission coefficient is 1 minus, and then this is going to be root 4, which is 2 actually. 2 minus, and then this has to be 16 in here, to the 4th, and then over 144. And I don't think that that's an incredibly nice answer, so let me go ahead and calculate that. Let's see, we got 1 minus 2 minus square root 16 to the 4th, divided by 144. Oh, it is an incredibly nice answer. It's about 8/9. Is that chill? Is that super? I kind of want to do the arithmetic now. We can factor out, well, 16 is just, the root of 16 is just 4. So we have that sort of thing going for us over 144, and that's 1 minus negative 2 to the fourth over 144, which is 1 minus 2 to the fourth is 16. Yeah, it's 16. Awesome. So if you divide both of those numbers there by, if you divide both of them by 16, aha. So 144 divided by 16 is 9. So you have 1 minus 1/9, which is 8/9. So, okay. That's a pretty funny transmission coefficient. And a pretty funny problem. Okay.